Let's get started. First, one more reminder for the course evaluation. This is where we're at right now, 33% or 4%. Okay, announcement for the final CTF. So we will have a 3-hour final CTF, and actually I plan to give you some extra time there. So it will be May 16th, Monday. You have to be here in person. There will be totally 5 challenges, and I will label those challenges, the difficulties based on my own understanding. It may not work for you, but that's at least how I feel they are easy or not. There will be no other written final exam. Also, there is no other multiple choices questions. So 3 hours, just CTF. So today we will keep talking about micro architectural vulnerabilities. We will talk about Spectre, which is very related to Meltdown. The vulnerability they are exploiting are very similar, but actually more vulnerabilities there, more optimizations we're using there. So as we discussed this Monday, out of order execution is a very useful optimization, make our CPU runs much faster compared to in order execution, which strictly process those instructions one by one in a sequential manner. The out of order execution, if the CPU has that, the CPU may execute several instructions at the same time, or some instructions, later instructions at an earlier time. As long as the CPU has the resources to execute that instruction. So here, look at the left-hand side. We have a very small C code snippet. So we have a local variable data, then we have a predicate x smaller than size. So x data size, they are all variables. It doesn't really matter local or global. Then if x is smaller than size, then data can be increased by 5. So that is a logic at the C level. So in this example, it's a little bit different from the example I showed you on Monday. So Monday, I showed you 2 examples with 5 instructions, and those instructions, there are no branches. They're just a sequential. Here, this example, even though it's a sequential level, not the assembly level, technically there are 2 branches, right? You can execute the branch where x is smaller than size, or you can execute a branch x is greater than size. And that, so what I want to say is, even in this case, even though there is a predicate, there are branches, the CPU can still do out of order execution. However, the CPU cannot execute the 2 branches at the same time. The CPU will choose one branch to do out of order execution. So, well, maybe future CPUs will be able to execute both, but right now no CPU can do that. We can only choose one branch and execute. So the comparison there, x smaller than size, those are 2 variables. So we know that there is no instruction for us to compare 2 memory locations. We have to load one of them into a register, then compare with the other one. The other one can in the memory or in register. Though there are instructions to do that. So the comparison x smaller than size actually has at least 2 operations. The first one is you need to load, let's say load the size into a register, then compare x with size. That's two different operations. And we know that load something into the memory could be slow, because memory is slow compared to register. If that data is already in cache, it will be fast. But if it's not in cache, it will be slow, right? So what the CPU really does here is, let's say the CPU will guess X is smaller than size. Later we will see how we will make CPU think that way, or make CPU always guess that way. We can actually train the CPU. CPU basically is learning which branch to take, and we can train it. So let's say the CPU guess we're going to take this branch. Then what happens is the CPU will do out of order execution to execute what is here. Data equals to data plus 5. And at the same time, the CPU will try to retrieve the data from memory to the variable size and compare that. If the comparison actually is correct, then the CPU will just commit what it has been executing out of order. Otherwise, the CPU will just kind of go revert back to previous state, which means the CPU will actually store the out of order execution information somewhere inside of the CPU. So a little bit different from the out of order execution is something we call the speculative execution. And you can see the name, that's where the vulnerability spectral comes from. So the speculative execution is just another type or extension of out of order execution, which we discussed on Monday. So this one cares about the branches. So when we say out of order execution, the example I showed you in Monday, there's no branches. So speculative execution is just it has the ability to issue instructions past branches. So it's basically an extension of out of order execution. So when the CPU does this, the CPU will preserve its current register states, make a prediction as to the path that the program will follow, and since it's a prediction, it's a guess, the CPU can make a wrong prediction. Then the CPU speculatively execute the instruction along the path. Sometimes the CPU can execute hundreds of instructions. Those instructions could be very fast. The predicate could be very slow. So it can be hundreds of instructions. So if the prediction turns out to be correct, the results of the speculative execution are just committed, putting into the registers. And because of this, the CPU didn't waste any time waiting for the results of predicate. However, if the prediction is not correct, the CPU will abandon the work it performed and reverting its state to including register state and also memory states. So that is how it works, from out of order execution to speculative execution. So like I said, speculative execution on modern CPUs can run several hundred instructions ahead, maybe because the predicate is very slow. Since work is done before it is known whether it is actually needed, it prevents a delay, it speeds up the CPU. However, there is also a big issue, which is, well, another thing involved with this one is branch prediction. So how does the CPU predict which branch to take? The CPU, there are many different mechanisms. Especially, we have seen several different kinds of spectral vulnerabilities, and I'm going to show you later. And the CPU has different mechanisms to handle those direct and or indirect and indirect branches. So how CPU gets that is based on the history. That's why we can train the CPU multiple times to give it some fake history, or the CPU is always going to take this path. Then when CPU actually executes another piece of code, then it will be forwarded to execute one path ahead. And that is how we can exploit this vulnerability. So there are several types of spectral, at least two. I think those two are the ones in the original paper. The first one is the conditional branch misprediction. So there is no indirect call, indirect jump here. Everything is direct. So there's an if, then there's something inside if, something outside. So when we compile this piece of code, we're going to get a jump, a conditional jump. Conditional jump is a direct jump. There's nothing indirect. However, we can train the CPU to believe, for example, it will always go inside this if. Then the second type of spectral, we're not talking about those direct jumps or direct calls. Instead, we're talking about indirect branches. For example, there's a call EAX. So we know that statically, if we analyze a program, we say call EAX or a register. We don't really know the value of the register, right? So sounds like there's nothing we can optimize. So at runtime, what happens is if that call EAX happens several times, the CPU will remember what was the value of EAX. So the next time it says another call EAX, the piece of instruction at the same location, what the CPU does is the CPU will remember what was the last time of the EAX and start the out of order execution. But the EAX may not be the correct value this time, right? So those are the two types of spectral, type 1, type 2. I believe there are more. I'm not sure if there are more types now. It depends on how people name it. So this has been discovered for 4 years. A lot of approaches has been proposed to try to mitigate this issue at the software layer. But technically, this rooted in the design of the CPU, so very difficult to fix. Okay, so we are going to say some comparison between spectral and Meltdown. So both vulnerability, the root cause of the problem is out of order execution. However, the out of order execution is slightly different. The spectral has the branch prediction involved as well. So Meltdown, the vulnerability, it's easier to fix. We talked about this Monday that if you do not map the memory location of the kernel memory location, it will be difficult for people to hack that. But the spectral is harder to defeat. And all of those two vulnerabilities, the root cause is when the CPU out of order executes some instructions and later find out it should not execute those instructions, it will roll back its register, it will roll back the memory. Those are good, those are correct. The problem is they do not roll back the cache. That's the root cause of the problem. But if the CPU is shipped, there is no way to modify that. Right? So next, we are going to look at some example code. We're going to use the virtual machine. I believe we can use this on the server, but we didn't post that. So we're going to use the virtual machine provided by CTF. And This is the first program, spectral experiment. Let's take a look. A very simple program. We have a main function here, a local variable I. The first thing we do is flash the cache. So there is so later we're going to measure the cache, but first we flash it. Then this is funny. We're going to train the CPU to. There is a function called victim. The victim function has exactly the same, well, slightly different code I showed you just now. There is a predicate if x is smaller than size. If x is smaller than size, we're going to bring use x as index and bring some data into memory. And we know that when we bring data into memory, it will also go to cache, right? So the x here is kind of like a secret. X is a secret, remember that? So size we define as 10. So if x is smaller than size, it will always go here. So then in the main function, we try to train the CPU to make the CPU think. Next time we say x, the x will still be smaller than size. Okay. So what we do is there's a for loop. In the for loop, there are 10 iterations, and each of the iteration we call victim, and we give it 0 to 9 as parameters. So for those 10 trainings, each of them is smaller than size. So each of them will take this branch. Okay. So after we train this, we flush size out of cache. Size is a global variable here. We flush it out of the cache. The purpose of this is so next time the program we use the instruction cl flush to flush out the size from the cache. The purpose of this is so the next time we use the variable size, the global variable size, so we know that it's not in the cache. It has to be brought back from the memory, and that will be slow. Okay, so that's the purpose. Then we also flash. This part is kind of like prepare for the cache. So I'm not sure this part is actually needed because we already did a flash side channel. Okay, what interesting is here is we make another function call to victim. But this time we give it a big number as a parameter. We have 97. So 97 is much larger than 10. So this time it's not supposed to go into this branch, right? However, what happens is when we call the function victim 97, when CPU get here, when CPU is executing this comparison, x and size, the CPU doesn't know right away the result. The CPU know x is 97. The CPU doesn't know what is the value of size. It has to get that from the main memory. But CPU doesn't want to waste its own units, doesn't want to waste any CPU cycle. So instead, it's going to keep executing. And we already trained the CPU to believe that it's very likely x will be smaller than size. So the CPU will keep executing this line, which is we're going to use 97 as index, bring some data to the array. Okay. Then later, so this time eventually the temp will never have the data we want when we call 97 because the CPU later realized it's not correct. However, that information will be in the cache. Okay, that's a problem. So then we do a reload here. This is a typical flash and reload. So when we do a reload, we measure all those memory addresses to say if those addresses have been brought into the cache, then we will find out 97 has been brought into the cache. So that is how, even though here the program is not reading the secret 97, but we will get the value 97. So that is the spectral. As you can, so you can see from the code. Interesting thing here is training the CPU to believe X is smaller than size. Okay, any questions? Everything makes sense. Let's take a look. Take a look. Let's see. Have the spectral attack. And let's use the spectral experiment.c code first. So you can see this is exactly the code I just showed you. We didn't talk about the reload part because we saw that last week. I already compiled this one. So if we run this piece of code, the first time we already got it, secret 97. The second time we didn't get it. You see? So it doesn't work every time, but sometimes it works. So this is the spectral experiment one, and let's take a look at the spectral. This share is so difficult. Okay, let's take a look at a little bit more complicated case here. So in this example, we have some secret. The secret is just a byte string. Even though it's a character string, it's the same as a byte string. Each character is just a byte, right? Then we have a sandbox function here. So the sandbox function is supposed to take an index for a buffer. The buffer is only 10 bytes here. You can see the buffer is only 10 bytes. And it's supposed to return a value in the buffer given the index. But the index you give could be a large number. You could give well, this is a size t, so you cannot really give a negative number. You can only give a positive number. So inside this function, there is a predicate check whether x is smaller than bound upper and also bigger than bound lower. So in this case means x has to be smaller than 9 and bigger than 0 for this function to return the value in that buffer. Otherwise, the function will just return. So this function gives you, well, but you can say here is if this function doesn't restrict the index you gave, it actually has a buffer overflow or buffer overrate problem, right? So even though the buffer is 10 bytes, technically you can give it a huge number and it will read something way beyond that 10 bytes. Say program allow you to do that. And because we have this bound check, it's not supposed to happen. Also, you notice that the bound upper and bound lower here, they are coded as global variables. Even though they are hard coded, 9, 0, and 9, they're coded as global variables. We didn't really hard code it here in the 0 or 9. Okay, I guess you at this point you probably already you can already guess why we do that. If we hard code here to 0 and 9, this comparison will be very fast. We cannot flush those two things out of the cache. You can guess what we're doing later is we're going to flush those two variables out of the cache. So when we execute here, we're going to retrieve the value from the memory, which will be slower. If you hard code this to 0 and 9, that's just the one instruction hard coded. You will not be slow. So this is the sandbox function to do that. Then we have the flush channel, side channel 1 standard, just to clean up, just to get the cache prepared, get rid of those noise. Then there is reload, the standard one. Now we have the spectral attack function. The goal of the spectral attack function is we are going to use that victim function, that bounded restricted access function, to read the secret. We're not going to read the buffer because that is allowed. The content of the buffer, that's allowed. We're going to read something that is not allowed, the secret, which is at some other address, not really the buffer. And this function is not supposed to give us that because it has a bound check. Let's say how this could happen. First, we will call that restricted access function multiple times. We train it. We just give it a small number, train it, make it believe it's going to, it's very likely to have a small number, and it's very likely to take this branch. Okay. So you can see if the X is huge here, we're going to read beyond the buffer. The buffer is 10, but we're going to read beyond that. Now after that, same as what we had just now, we were just to flush those two bound checks. Flush those two global variables, where we also flush the cache. Then after that, we are going to call this restricted access function one more time. And this time, the index beyond will be something much bigger. So S is going to give us the secret, but well, technically S is not going to give us a secret, right? Because this is a restricted read function. But when this executes, that will be put into the cache. If we check the main function, we can say we first print out the address of secret, we print out the address of buffer. Then we print out the index beyond, which is actually the address of the secret minus the address of buffer. So we get the difference from the first byte of the secret and the first byte of the buffer. So if we use that value of the index, we can read the value of the secret. Make sense? Then we just use a spectral attack to read that, and eventually it's this read. If there's no cache side channel, if there's no spectral, this should never work. But if we run this on our machine, we'll see that this time we run it, didn't work. All right. We get the connected number. So we actually have a lower end of the buffer. For how many of you know that you can't go back to the index in C? So that will allow you to do that. I just don't care. Okay. So demo multiple times. Now we get it. 83. Let's say check our code if the secret is 83. S is S 83. Let's check ASCII. ASCII table. Uppercase S. See, uppercase S is 83. We actually read the value of the first. So it works. So in the homework, oh, it actually stays here S. In the homework this week, what you are going to do is you're going to extend the program a little bit to, instead of just reading one byte, you're going to read all bytes, all the secret here. Any questions? Okay, that's basically how Spectral works. Let's see. I actually do not have more slides on this one. How many of you downloaded the virtual machine last Monday? Will you be able to run that Meltdown? Haven't tried? Okay. So you guys can keep doing that. Meltdown will be homework of this week. Spectral will be homework of next week. So next week we're going to talk about risk condition, and the last class we're going to summarize what we learned this semester by showing you a keynote speech given by a professor at CTFs last year. So we're going to watch a video at the last class. So he covered in 1 hour, in this 1 hour keynote, he talked about many things we discussed in this class. So I want you to see the questions there. Okay, so we're going to work on Meltdown. I will post the homework of this week. Basically, it's Meltdown one. So that's going for next week.